Let's go through the answers to worksheet 2. Problem number 1 has an incident wave moving to the right. Remember, the incident wave is the wave that goes into the barrier. The reflected wave is the wave that bounces off the barrier. So in this situation, this incident wave, when it hits the barrier is going to act as a fixed end. So we should have fixed end reflection. And you'll recall that in fixed end reflection, the pulse or the wave flips or it inverts. So the incident wave is on the top, and in fixed end reflection, it flips. So now it's on the bottom. This is going into the barrier, and this is going away from the barrier. Now let's look at free end reflection. In free end reflection, the pulse or the wave stays on the same side. So the incident wave is going to the right and it's on top, and the reflected wave is going to the left and it's also on the top. So in fixed end reflection, the wave flips, and in free end reflection, the wave stays on the same side. So let's again look at fixed end reflection and free end reflection. Look, the wave has flipped. This wave is traveling to the right. This wave is traveling to the left. Now, this can be tricky for students. Notice that whatever strikes the barrier first is what leaves the barrier first. So, for example, this flat edge is going to strike the barrier first before this angled part does. So if this flat edge strikes first, the flat edge leaves first. So notice that the flat edge is leaving first. Same thing is true in free end reflection. If the flat end strikes first here, the flat end also leaves first. So the difference between fixed end reflection and free end reflection is that fixed end reflection, the wave flips. Here it's on the top, now it's on the bottom. In free end reflection, it stays on the same side. So the wave is on the top, the wave is on the top. Two students, each holding the end of a slinky, are 5 meters apart. It takes 0.6 seconds for a transverse pulse to travel from the student generating the pulse to the lab partner at the opposite end of the spring. So you got that? We have two students, they're 5 meters apart, and one student sends a wave to another student. And it takes this long for the wave to be, for the wave to reach the other person. How long will it take the reflected pulse to return to the generating student? So you see we have a student over here and a student over here. A wave is sent. It takes 0.6 seconds to get to this student. How many seconds will it take to travel back to the student that generated it? Well, this is where you have to remember that the only thing that influences the speed of wave is the medium. The medium hasn't changed. It's the same medium, so it's the same velocity. That means it will take the same amount of time. So 0.6 seconds each way. A second pulse of twice the amplitude is sent. Will the pulse take more time or less time or the same amount of time to reach the end? This tricks students. They think that a pulse which is bigger is going to go faster. That's not the case. Remember, the only thing that dictates the speed of a wave is the medium. And we haven't changed the medium, so it's the same time. Now the students move so they're further apart. So it stretches that slinky as they move further apart. Compare the speed of a pulse on the more stretched spring to the speed of the pulse when they're 5 meters apart. So what happens when they stretch that spring? When they stretch that spring, what they've done is they've changed the medium. They've increased the tension. So if you increase the tension, the speed of the pulse is also going to increase.